I'd like to first thank the organizers for the invitation and excellent hospitality here. Various speakers have claimed uniqueness, but I think in my case I don't have to reiterate the point, it's pretty obvious and accurate. And probably I'm the only participant who have to struggle through a visa process. There's some other claimed uniqueness. Anyway, so I'd like to talk about some aspects of p-adic string that I've been looking at. There are actually roughly two parts that the talk will be broken into. In one part, you really don't need anything about p-adic strings. It's I talk about some non-commutative solitons in a non-local field theory, and that's nothing to do with p-adic. It's an ordinary field theory in space-time. And then in the second part, which is based on work done in collaboration with Federico Kawano at Tokyo University, I'll look at some possible microscopic origin of this non-commutativity that comes from p-adic string. But given the time constraint, I may have to rush through this part. And also, I have probably far too many slides, but fortunately for me, many of the talks earlier have covered various aspects. The review that I was thinking of doing, but that won't be necessary. So roughly the plan of the talk is that I will spend some time on motivating the questions that I will be looking at, then a very brief lightning review of this p-adic string theory, and then I will go into this non-commutative solitons that can be found in these theories. At the end of which I will review, I'll tell you about the BW2005 limit and how it reduces to ordinary string theory, at least one string field theory approach called the boundary string field theory. A very short comment on multi-solitons because I don't know about it. And then in the second part I'll go into the microscopic origin of this non-commutativity, whether it comes from a wall sheet B field or not, as in the usual string field case. And I'll tell you that it's actually rather easy to couple the B field in the minimal way that's done in ordinary string theory and find the Green's functions. But there are some subtleties and problems so that you don't really get the non-commutativity that you put in by the usual non-commutative deformation at the effective field theory level. Finally, I will just summarize and make a few remarks in this time. So as you know, the non-commutative deformations of quantum field theories have been studied rather extensively in the last few years, and they exhibit very remarkable properties. And most of there have been some talks already, and most of them have focused on perturbative aspects of these theories. But I'll talk about finding some classical solutions, so therefore non-commutative behavior of these theories. Typically, one starts with a local field theory and does a non-commutative deformation to get a non-local field theory. But there are many field theories which arise in particular in the study of string theory. For example, string field theories are non-local to start with. And so we'll take one such theory and do a non-commutative deformation. The particular theory that I have in mind is called the effective field theory of a scalar field, which is the tachyonic scalar on the d-branes of the so-called p-adic string theory, which was proposed by Freund and collaborators in the late 80s. In fact, this string theory is rather an interesting theory because it's at least a sector of this theory is exactly solvable, and one can, by exact solvability I mean that one can find all the correlation functions of this scalar field. This is what was mentioned by Alexei Morozov as the dream of quantum field theory, that you find all correlation functions in a field theory. That's possible in this case, and therefore one finds an exact effective field theory of this tachyon, and which we can now use to check the conjectures made by Sen about the behavior of the open string tachyon. So for this reason, and perhaps for other reasons, p-adic string theory could be a useful guide to answer difficult questions in usual string theory. And just like non-critical string theories are useful toy models, similarly p-adic string theory could be a useful toy model. And moreover, as I mentioned, and you'll see it again, that in the p going to 1 limit, rather unexpectedly, it turns out to be the usual string theory again. So therefore, studying p-adic string theory might give some good idea of the dynamics of the usual string theory. For that, however, we really need better understanding of this string theory itself, about which not so much is known. All that we know is really the properties of its debrane in flat space-time, and that too mainly restricted to the tachyonic sector, as I said before. So the question that motivates us is how about putting p-adic string theory in non-trivial backgrounds? And in general, you can think of putting in curved background which comes from a closed string condensate, or some open string background like electromagnetic field. And I consider the simplest case of this, which is the constant background of the B field that you get from the closed string set. We know that this provides a non-commutative deformation of the effective field theory in space-time, and at least for the first part, I'll proceed with the assumption that this is precisely what happens in the case of p-adic string theory, by which I mean that I'll take the effective field theory of the tachyon and do a non-commutative deformation of that theory. I'll use the silly abbreviations, but I always say tachyon when I mean p-adic tachyon, and string when I mean p-adic string in solitone and so on. So let me very quickly tell you what a p-adic number field is, because this may not be the most familiar object, but I'll skip much of the details in the next few slides. So basically you start with the field of rational numbers and give it a different topology by proposing a different concept of distance among the rational numbers, not the absolute value distance, concept of distance that comes from the absolute value of the difference of the rational number. So for that you have to start with a prime number, any of the prime number that you fancy, and then for an integer, you find the highest power of this prime number that divides that integer. This could be 0, because many of the integers may not be divisible by that prime number at all, and it could be any other integers, and that is called the order of that integer. And the p-adic norm for an integer is simply p to the minus the order of that integer. And if it's a rational number, since it's the ratio of two integers, this is just the order is just the orders. So it turns out, which I will not get into, that this is actually a consistent concept of length on rational numbers, and this has rather unusual properties from usual lengths. In particular, the triangle inequality is replaced by a stronger triangle inequality, which gives it so-called non-Archimedean property, that if you take some, in the usual case, if you take some interval and repeat it n times, then that length just increases. In this case, that is not so, and that leads to many counterintuitive properties, but let's not get into that. You start with this concept of distance and put in all the limit points that you get from Cauchy sequences, looking at the Cauchy sequences, and complete this set of fields to get this p-adic number.
You said before that you wanted to take the p goes to 1 limit.
Yes.
But p is equal to 1 is the prime.
No, it's not a prime.
So how does that?
I'll come to it.
Oh.
Please have some patience. Okay. Any number? Okay. Let's not get into this. It's not really central to the part of the talk. But the point is that one can do analysis on the field of p-adic numbers, and you can consider functions which are valued in p-adic. So that is, the domain and the range are both p-adics, or you can have complex valued functions. So for the first part, I'll really consider complex valued p-adic functions, so that the space-time the string lives in is usual space-time. So therefore, the effective field theory that we have is also for tachyon moving in usual space-time. So what is p-adic will come to later. And this theory was what was proposed by Freund and collaborators, and generated quite a lot of interest in the late 80s. The way they proposed it is rather ad hoc, and let me proceed it that way for the moment. The Koba-Nielsen formula for the tachyon amplitudes involves some integrals which are integrals over the boundary of the worldsheet, which is over the line or the circle, depending on whether you prefer the disk or the point plane. And these are the integrals that we have to solve. In the case of ordinary geometry, it turns out that this integral of these integrals, the only integral that you can do explicitly is the 4-point function, that is n equal to 4, and this is again only for tachyons. So these people propose that instead of these integrals, you consider the integral over the p-adic line and replace these absolute value norm of these integrands by the p-adic norm that I just reviewed for you. And the advantage of that is that in the case of p-adic, unlike in the case of real numbers, all these integrals for all n can be explicitly calculated. So that means that you know all the endpoint functions of the of this theory, and therefore you can write an effective field theory in space-time for this tachyonic scalar of the p-adic string theory. And this effective field theory will be an exact effective field theory because you have derived it from the knowledge of all the endpoint functions of this scalar. So it's actually summarized also in the form of a very very nice action, which has some, at least at formal level, it has some resemblance of the action that you get from the string field theory tachyon in the cubic string field theory approach. For that, it's best to actually shift and rescale the field from the original tachyon T and write in terms of this field phi, which is defined in this particular way. And in terms of this field phi, there is a term which is phi exponential D'Alembert phi, and there is a interaction term which is phi to the p plus 1, depending on the p that you start. And this is the effective action that will be our starting point. Now, and to answer your question here, I like to mention that after you do the integrals, you can do the integrals only for prime p, but after you do the integral and write this effective action in space-time theory, you can consider any integer values of p. But that still doesn't tell you how to, when you cannot put p equal to 1, then you don't get anything sensible. But formally you can substitute p equal to 1 plus epsilon and take epsilon into 0 to get the p. So that's what we'll do later. So this kinetic term is actually non-standard and involves this non-local factor, and the potential has this kind of behavior that most of the primes are odd. So for that, the potential is given form like this, and if it's even, you can take an integer dimension, you get some potential of this kind. It has pathological singularities on both sides, just like the ordinary bosonic string, but we'll ignore that and look at the dynamics only in this region from this maximum to the minimum. So the equation of motion is the exponential of D'Alembertian on phi is phi to the p. The solutions to these equations are constant configurations. Phi equal to 1, which is t equal to 0, the original tachyon field. So this is naturally identified with the d brane that you start with. That's the vacuum solution for this. And you can define the tension of the brane by the energy of this configuration, and that's this. And there is another constant configuration. If you go back to the potential, the one that I described now is at the top of the potential, phi equal to 1 or t equal to 0. And there is another constant configuration which is phi equal to 0 or t equal to whatever value that is. It's easy to check from the form of the kinetic term, which is just phi exponential box phi, that there is no perturbative excitation around this configuration. So this is what was conjectured by Sen and was reviewed in Vrnjačka's talk yesterday, and by actually shift of the energy, you can put that energy, you can set that the energy vanishes in this configuration, or you can just measure the difference between the energy of the maximum and minimum. So it would be natural to identify this vacuum as the closed string vacuum according to the conjectures, except that we know nothing about the closed string version of the p-adic string. So apart from these constant configurations which are interesting for this check of conjectures, there are also space-time dependent solutions which lets us check the other part of the conjecture, which is that starting with a sufficiently higher dimensional brane, you can consider some kind of solitonic objects on this brane of this tachyon theory, which are lower dimensional branes. So for that, it's actually very useful to notice that this equation is trivially separable in Cartesian coordinates. So all that you could do is to find a solution of this equation, and that has a non-trivial solution, which is in terms of an exponential, a Gaussian exponential, in which the amplitude and the spread of the solution are related, and they are given by some functions of p. So since it's separable, you can just take a configuration which is a Gaussian lump in some of the directions, which are called the perpendicular directions, and take the trivial configuration in the other directions. So this will give you a solution in which you have a configuration where the energy is localized around the hyperplane x perpendicular equal to 0. And this is what we'll naturally identify with a D brane, which is say D M brane, which has so many transverse directions. So again, we can compute the energy of this and compare with the energy of a higher dimensional brane, and find that these ratios of these tensions are independent of any particular value of m that you have, exactly as in ordinary string theory. So you can also study a world volume theory of the soliton by looking at the collective coordinates of the soliton, and again you can do a consistent truncation of the theory and compare with what you know from pre-adic string theory. So this was what we checked some time back and showed that this is one toy model where you can explicitly prove the conjectures made by SEENET. So what I'll do now is consider a non-commutative deformation of this theory, and non-commutative field theories have already been reviewed, so I can skip this part. And mention that, say for example, it was shown by Gopakumar, Minwala and Schrodinger that if you take a scalar theory of a single scalar field phi and do a non-commutative deformation, and the potential has some kind of generic form like this, that there are soliton solutions which are possible in this theory in the limit of infinite non-commutativity. That is, if you take the non-commutativity parameter theta going to infinity, then this ordinary scalar field theory in any dimension admits soliton solutions. It doesn't violate knowledge from Derrick's theorem or something, because these are non-local theories. So the simplest of these soliton solutions is again a Gaussian solution, which is whose width is proportional to theta and whose amplitude was a fixed number. And more generally, you can find solutions by going to the operator correspondence and demanding solutions of projection equations. Again, something that was reviewed in yesterday's string field theory talk. The point is that these solitons become unstable at some finite values of theta. As soon as we start deforming away from theta to infinity, these solitons become unstable. And that's not unexpected, because we know that commutative, say, pi4 theory or pi3 theory does not have any soliton solution. So it's not unexpected that these solitons are unstable, and that's true of not just this Gaussian but all these kind of solitons. And in fact, I should just mention again here that these non-commutative solitons have been used in string field theory to understand the dynamics of these tachyons by various groups of. So what I want to just mention here is that this is a Gaussian solution, and the p-adic, commutative p-adic string theory case also what we saw is a Gaussian solution. So it's kind of suggestive, and you might expect that there will be a relation between them, and that turns out to be the case, as I just tell you now. So we just by hand do a deformation of this effective action. So we just replace all the ordinary products by this Moyal star product in this action. And this is what will define non-commutative tachyon for us. The equation of motion, the first part is the same, the reference side is the same. On the right hand side we get star product of pth star product of phi. And for simplicity, I'll just put non-commutativity along two directions, x1 and x2, and look for solutions only in that section. The constant configurations are still solutions of these deforming equations of motion. And it turns out that also the space-time-dependent lump solutions survive as solitons, except that soliton solutions, except that they also get deformed because of the non-commutativity. And the main reason why that happens is that the star product of Gaussians, two Gaussian functions, is again a Gaussian function where the amplitude and the width changes. So all that you have to do to find the solution is to make a Gaussian ansatz and then equate the left-hand side of the right-hand side to find the amplitude and the width of the Gaussian number. That's rather easy to do. And you find that the width is determined by a polynomial equation of degree p of this form. This involves the width a as the unknown, and in terms of this function, in terms of the non-commutativity parameter theta, you can solve. Except that an arbitrary degree polynomial of this kind you cannot solve in closed form. You can look for graphical solutions, and in the case of the commutative, in the commutative limit, it's a linear equation which you can solve explicitly, of course. And otherwise, as you increase theta, you find that the root shifts towards the origin, and it becomes it goes to a tends to 0 in this case, which is the expected result, because we know from the GMS solitons that in the limit of theta going to infinity, it should reduce to the GMS solitons in where the width a goes as 1 by theta, as we showed the form of the equation I showed earlier. So you can check that this is indeed what happens, and you get the commutative limit. So what you have here is the width as a function of theta, which you can plot and see that it plots up as 1 by theta. And once you know the width, you can also find the amplitude of the solution, and that again is determined by as a function implicitly as a function of theta, because a itself has to be found as a function of theta. And this function again you can check that it goes in the commutative limit to the p-adic amplitude that you know from the p-adic solitons, and on the large non-commutativity limit you recover the value given by the GMS solitons. So in summary, what we find here is that non-commutative solitons interpolate smoothly between the non-commutative soliton without a p and the commutative soliton with a p. So how do you get the p going to one limit? As I mentioned before, that you take p, set p equal to 1 plus epsilon and take epsilon going to 0. There are some terms which like 1 by epsilon can cancel between the kinetic and the potential term. So you throw away that piece, and the final piece is what you keep, and you find that you get field theory which is a standard kinetic term, but a non-standard potential term. And it turns out, rather unexpectedly, as was pointed out by first by Gerasimov and Shatashvili, that this is precisely what you get from one approach to string field theory called boundary string field theory, if you truncate the action of the tachyon to only 2 derivatives. So that's the Lagrangian exactly. And now we'll deform this theory by this non-commutative deformation, which we also studied by these two group of people independently, and they studied some aspect of this. So the equation of motion is now, as usual, is replaced by it replaces ordinary multiplication by the star multiplication, and it has constant configurations as solutions, and it also has Gaussian lump solution. The point is that you can make this Gaussian ansatz, and what you need here on the left hand side is simple, so that's just ordinary case. But on the right hand side, you would need the star log of an ordinary exponential, not a star exponential. That you can define as the way we got this t going to one limit, which we just define the log as by its this definition as a limit in this way, and by comparison again, as in the case of a value of p, you will get the weight and the amplitude as determined by this time by transcendental equations. Once again, you can check that these interpolate smoothly on the two sides, from the commutative to the infinite non-commutative. So about multi-solitons, actually I don't have much to say, except that this Gopakumar, Stradlin I forget his last name, Matt studied these solitons, and Hedrick studied these solitons, but in the case of p-adic, actually these don't, these or some generalization of these don't turn out to be solitons. There may be some other approach to it which I do not know and didn't consider, which will be some kind of multi-solitons in the p-adic case. That's important because in the case of p-adic string theory, actually we do not know anything about these Chant pattern factors or gauge fields on the p-adic string. So it would be nice to get some multi-soliton generalization and look at that aspect. So now I go to the second part, and I fear that there is not much time on that. In the case of usual string theory, the non-commutativity comes from a constant B field. So the question that we want to address is that, is there a microscopic origin of this non-commutativity in the case of p-adic string? And it's rather interesting that although the way the p-adic string was originally proposed was this ad hoc substitution of the Ober-Nielsen amplitudes in the form of integrals by their p-adic counterpart, shortly after the work of this group of Freund and collaborators, Zabrodin and collaborators actually found a nice worldsheet description of this p-adic string. So the worldsheet description is as follows. Instead of the disk as the open string worldsheet, you have a Bethe lattice, an infinite Bethe lattice, which is actually a lattice in the sense that it's actually a tree. It doesn't have any closed loop on it. And the description is as follows. For a particular value of p, say in this case p equal to 3, you have you start with some arbitrary point c, and then that branches into 4 points. So you have 4 nearest neighbors, and that further branches into 3 points, and you just repeat this process ad infinitum. These lattices are very popular in statistical mechanics because they allow you to solve various models, statistical mechanical models rather easily, and that's the description these people form. So they propose that if you start with this lattice, and they showed rather, that and take the standard discretized Polyakov action on this lattice, you will get the Ober-Nielsen amplitudes of the p-adic case. I will not go into that, and now I have to skip a lot of stuff, but the point is that instead of working with this Polyakov action on the Bethe lattice itself, what you can do instead is to integrate out the bulk of the worldsheet to get a non-local action on the boundary of the worldsheet. And that was found actually before the group of Zabrodin and all by 3 independent group of people, and that's a non-local action on the boundary of the worldsheet. As an integral operator, but that's not very important. But I want to mention here that in the case of usual string also you can do the same thing, and you get a non-local action on the boundary of the worldsheet, which is exactly of the same form when you replace this p-adic number by real number and the p-adic norm by real norm. So this will be more useful to us because we haven't found a way to couple the between the bulk of the disk, but rather you can put a coupling on the boundary by noting the fact that a constant B field is equivalent to a linear gauge field on the boundary of the worldsheet. So that's the main observation, and once you couple that extra term on the worldsheet, that you get an action which you can write. So I'll skip some of the details here. But the action with the B field is, in addition to the term I showed you just now, there is an additional piece coming from the B field. But the point is that even with this B field present, you can easily solve for the Green's function, and you get a Green's function which looks like the case of the ordinary string theory. It has a log piece and a piece which depends on the sign function, and you can follow exactly the description set out by Schomerus and then by Seiberg and Witten, and study these things and find all the correlation functions that you need. So by this you can put a formal, you can derive the non-commutativity formally, and that's the result that you will get. But there are caveats because of the absence of a natural notion of ordering in the field of p-adic numbers, and you don't have an action which is this Mobius invariant when you couple this B field. That's true even in the ordinary case, because this B field actually destroys the full projective invariance. It only keeps the projective invariance which keeps the order of your vertex operators the same. So up to cyclic ordering you have the residual Mobius invariance. But in this case, because of lack of ordering, these issues are very complex, and because of lack of time, I'll skip all that. Only I mentioned that you can calculate the scattering amplitudes, and you get from this approach you get some result which matches qualitatively what you get from this field theory deformation, but not quantitatively, as you can see by comparing them. But it could be that this minimal coupling of B field is just just one of the couplings, and you have to add some other directions to this. It could be something else, I don't know, but the question remains open. So let me just summarize quickly. What we studied was a non-commutative deformation of the exact effective action of the p-adic tachyon, and found a family of Gaussian log solutions which at all values of the non-commutativity parameter which smoothly interpolates between the commutative p-adic soliton and the non-commutative soliton of Ghoshal et al. In both cases, they owe their existence to the infinite number of derivatives in the equations. There is a meaningful p going to one limit in which you recover the usual bosonic string field theory, and then we looked at the possible microscopic origin of this non-commutativity. I want to stress that these solutions are actually unlike other exact solutions which do not have a smooth commutativity. In this case, because the p-adic string had a soliton solution already, there is a smooth commutativity. So there are various open questions. The most important among them is the role of closed p-adic strings, about which, as I said before, that almost nothing is known. And one can possibly use this non-commutative deformation to calculate the tension of the D-plane from, like the calculation of Polchinski's, like the calculation of Polchinski's original paper, which has not been done in the p-adic case. So thanks for your attention.
I have a question about this vacuum phi equal to 0 in the commutative case. You said that there are no any prohibited excitations around this vacuum. How do you see this?
Well, the kinetic term is phi e to the minus box phi. So you just look for poles of that property. There is none of any finite part of the momentum plane. So there is no finite energy excitation.
But it seems that you expand this propagating to get the usual kinetic term like phi or partial phi, right?
Yeah, but that's only one of the terms. You can solve the solve the Green's function exactly, and that doesn't have any finite any pole at any finite point of view.
I have a few questions, but just to prevent maybe possible questions to me after that, so I will just choose a few ones. So what about adelic strings and adelic approach? Because you speak here about translation from p-adic string theory to the ordinary string theory with taking p tends to 1. So what is your opinion about this approach? You know that this approach attended many, there were many attention.
This question is rightly asked to you after.
Okay, and the next question, what is about relation between non-commutative and string theory and p-adic string theory? Because we just have, and for some concrete value of theta, we have the same solutions.
That I think is rather a coincidence, because the it matches the solidaric solution, which is strictly true for infinite value of theta. And it just happens to match the p-adic solution for finite value of theta, which I think is a coincidence. I don't think that is.
So you think there is no some relation on a deeper ground between non-commutativity and non-Archimedean spaces?
I don't know. There have been some discussion about possible relation between p-adic deformation and non-commutative deformation, but I don't really know much about what can be done. At least in this case, I do not see any relation.
So at least at this point we know well.
Was there any problem with about loops in the CPS? All these calculations were recalculations.
Higher loops, p-adic string. Well, you know that since those papers of Vrnjačka and collaborators like